Hello and welcome to this first lecture on the new section on considering stochastic games in this course, Master in Game Theory. So, in this section, we'll give you an in-depth view of how to consider stochastic games. And we will begin in this lecture talking about how to account for these random events and probabilistic transition between states in dynamic strategic interactions. And what does that mean and how do you do that? Just hold your horses. We'll go forward and talk to you. So how do you think you can account for random events and probabilistic transition using stochastic games? Any thoughts? Anything that you have learned, you remember? Right. So accounting for random events and probabilistic transition between states, between one state to another in dynamic strategy interactions can be approached using two methodologies. One is what is called Markov decision processes. We will term them as MDPs. And second is a pure stochastic games. Now, what do these do? These frameworks allow for modeling of decisions in environments where outcomes are partly random and partly your control as a decision maker. Now, any thoughts on how can you incorporate these elements into strategic interactions? Let's take a look at that. So let's take a look at the MDPs first, Markov decision processes. Now, MDP is a mathematical framework for modeling decision making in situation where the outcomes are partly random and partly under the control of the decision maker. And what are the elements of MDP? As you see here, there are states S0, S1, S2, and these are finite set of states representing all possible situations in the game. And then there are actions A0, A1, two of them here. And again, these are finite sets of action available to the decision maker. Then for each action, there are transition probability. As you see in the top left, A0 you can has a probability of reaching S0 if you take A0 action 0.5 and reaching S2 as 0.5. Similarly, A2 if you take A2 action, the probability of reaching from S2 to S0 is 0.4 and from to back to S2 is 0.6. So like these are the transition probabilities. Then the rewards. Immediate rewards received from transitioning from one state to another state. As you see the zigzag arrow at the top and on the left side, +5 and -5. And there is a discount factor not given here, representing the importance of the future rewards. So that's a Markov decision process component structure. Now, how do you solve an MDP? There are two things you need to do. You need to iteratively update the value of each state using Bellman equation. And what that equation is, that's what we will spend in the rest of the lecture. So one approach is what is called value iterations. For each state, you iteratively update the value. The second is what is called policy iteration. You improve the policy. You have a policy that guides the decision making. Now you iteratively improve that policy, the actions to be taken in each stage until it converges. And convergence is a very important concept, very useful concept in deciding when have you reached, when should you stop iterating. So these are the two things you need to do, and we will look at in subsequent lectures each of this in a lot more detail. So we talked about the Bellman equation. So what is Bellman equation? So as you see on the left here, Bellman equation is a fundamental recursive relationship in dynamic programming and is used to find an optimal policy in a Markov decision process. It breaks down a complex decision-making problem into simpler sub-problems. And what are the components? What does each of these terms mean? VS, max, R, bracket, SA. Let's take a look at that. So the small s represent the state, right? It's a specific situation or configuration in a decision process, and you can connect it back to the earlier thing that we shows of the figure that we showed of an MDP. Action A is a decision or move taken by any agent, a player, right? The transition probability P of S dash given S and A is the probability of transitioning to state S dash from S given an action A. Again, we saw that earlier in the reward R given SA is the immediate reward received after taking action A in state S. So contingent to taking an action A in S, what is the reward you get? Lambda here is or delta is a discount factor between 0 and 1 that represents the importance of future rewards compared to immediate rewards. And finally, the VS is the value function, the expected discounted sum of future rewards from state S, right? And there could be multiple states, so you could have multiple value functions for each state. So that's how the Bellman equation represents the value function. It's a maximum of the reward of when you take an action A in given state S and a discounted value by lambda of sigma of the future value stage multiplied by the probability, simplified that way. So let's look at the notations once again. Vs is the state value of state S representing the maximum expected return, starting with status S and following the optimal policy thereafter. Max A indicates we are looking for an action A that maximizes the expected return. R bracket SA, immediate reward received after taking action A in status. Lambda is a discount factor which determines the present value of the future rewards. PS hyphen as apostrophe given S and A is the transition probability, representing the probability of moving from to state S from the state A S after taking action A. So moving from state S to state S hyphenated after taking action A. And sigma S apostrophe is the summation over all possible next states S dash, S apostrophes. So having looked at the Bellman equation, what do we do next? Now we will see how to do a value iteration in the next lecture using that Bellman equation that we talked about. And how can we solve that MTP by doing that value iteration. So thank you so much for watching this first lecture and considering stochastic games. I hope you're beginning to learn again new things, beginning to enjoy. And I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. Please do download the PDF file and take a look at specifically that Bellman equation. That is a thing that we will use very frequently as we go forward in all stochastic games. And do reach out to me for any help needed anytime.